Brown's gas generators. Cool deal. 335, no? Good afternoon, ladies and gentlemen, and welcome back to the Extraordinary Technology Conference 2017. This afternoon, I'm going to introduce you to a man. He's spoken before here, Tad Mauney. He's going to be speaking on open systems thermodynamics and free energy devices, a little bit of a departure from what he has spoken on before. He grew up surrounded by wires and bottles for his investigation of electricity and chemistry. He studied chem at U of A, Colorado State, and the University of Antwerp. Excuse me. So I would like you to give a warm welcome to Tad Mauney.
Thank you, Vern. Good afternoon. I'm glad to see you here. I hope that at the sleepy time of day, just after lunch, we can manage to make thermodynamics, which is sometimes close to the most boring part of science, something that at least doesn't put us all to sleep. And along the way, I'm going to ask my friends over here to find the laser pointer and the mouse. In the meantime, let me talk in general about the concept of free energy. If you live in a forest, you burn wood because it's there for your energy. What does that energy cost you? Nothing. The wood's there. It's all free. Okay, maybe, well, just sometimes you can just pick it up. But, okay, if you buy it from somebody who cuts it for you, now the energy costs, right? So you have to pay the cost of somebody to cut it for you. If you have solar panels, like we were just talking about, if you've got a solar installation, does the energy cost you anything? No, the panels cost you. But for you, the energy is free. It's not free to the sun, but it's free to you. So our perspective about what's free energy and what is expensive energy is really distorted by how we acquire it. And so if we come to invent devices that can deliver new sources or energy from new sources, the device is still going to cost something, even if the energy is coming from a place that, at least as far as apparent to us, the energy itself doesn't cost us anything. Okay, so the basic ideas of thermodynamics are that heat and other forms of energy act in ways that are consistent. And therefore, it can be understood and it can be described mathematically. Now, let's see, it was 3 years ago I talked here about some of the background of how the modern science of thermodynamics evolved, and you can buy that DVD if you want to. But basically, the scientists of the 19th century, in 1850s through 1890s, were really trying to characterize the machines that were being invented and find ways that they could describe how does it work, like a steam engine, and how can we make it better. So they found that energy can be converted, obviously we know this, converted between different forms, from heat to the pressure of the steam to mechanical work. and then eventually from heat of the fire to electricity, and the electricity to mechanical work or to lighting, and that as it's interconverted, that the conversions can be made more and more efficient. And so people with a great deal of trouble, actually, measured the conversion coefficients. For example, it took Joule in England probably about 30 years of measuring. What he did was build a device that had paddles in it, and they stirred a bucket of water. And he very, very carefully measured how much mechanical energy it took to raise the temperature of the water by a certain amount. And so he had to put a weight on a rope and let the rope turn the paddles, and over a period of decades he refined those measurements and closer to the modern accepted value. But the point is, this is not easy. It's very, very fussy work. And so the fact that under some conditions you can get this to be reproducible is itself remarkable. Okay, the question is, can we use the science of thermodynamics to study free energy systems? How many people, if you care to, have heard of the cases where somebody has a working invention? It seems to produce a useful energy output. They go to their investors. The investors say, yeah, we're into it. We'll be glad to give you 10, 20, 30, $100 million. But we just need this one thing. We need some physicists to tell us that our investment is safe. And so you take your invention, or some inventor took his invention to the physicists, and they looked at it and they said, well, that violates the second law of thermodynamics, therefore it can't exist. And since it can't exist, whatever it's doing isn't happening, and no, the investment's not safe. Okay, heard of that story? Okay, anybody who cares to say that they've had it actually happen to them personally? Close enough, first-hand acquaintances? Okay, it hasn't happened to me personally, but yes, I have first-hand acquaintances to whom it has happened. Now, what's the problem here? The theory has taken over and replaced the experiment. And so what we have to do is bring this back, that the purpose of thermodynamics is to elucidate what is happening in the observed phenomena, not to dictate what the phenomena are. Okay, basic ideas. Consistent rules of energy flow have been described, and these few phrases are called the laws of thermodynamics. And under certain circumstances, they can be tested very well, and they prove to be very, very accurate. But like I said, it's a very fussy business, and therefore our understanding might not be complete. Okay, there is a strong analogy between accounting for energy and accounting for money. We assume that energy has quantity, that we can apply mathematics to it, and we should be able to make it add up. Closed systems, the classical thermodynamics, the net change of all together, the mass, the energy adds up, and it doesn't change within the system. Open systems means that there can be a change. Strictly speaking, you could say that if you can define a boundary within which energy and mass are conserved, you have a closed system. But it doesn't matter where that boundary is. It could be the edge of the solar system. It could be the edge of the universe. Okay. The classical assumption that the energy of the system is constant. There is what's called the total energy. The total energy of the system. The internal energy of the components, the pressure and the volume, and the temperature and the entropy of the system. That would be closed. But Nobel Prize winner in chemistry, Ilya studied extensively the formation of the production of entropy, and he says thermodynamics, these potentials, the free energy, and this only exists under exceptional situations. In other words, it really only exists in equilibrium. But every living system, every evolving system is dynamic. So I'll take just a few examples of purportedly free energy devices, but let me back up a little bit here to point out something about, let's say, conventional thermodynamics and what it has been useful for and how it really has helped us make sense of things. So if I can we switch to the overhead device here for a second? If we take some ordinary water, and we put into the water something that we want to dissolve in it. Here I'm getting myself out of order. My nice digital thermometer had an unfortunate event happen. The water's about 70 degrees, just the temperature of the room. So we put our stuff in it. Stir it up a little bit. And say, what is causing this stuff to dissolve into the water? Well, basically the explanation is we need something better than it just does. So I say, it's like, Tad, it just does. Don't ask questions. No, we say that actually in the solid state, it's in a higher energy form than in the dissolved state. And so it goes downhill like a river from the high energy state to the low energy state. And in so doing, it changes into a new form, which is the dissolved form. Okay. So in a matter of a couple of minutes here, it's gone from about 70 degrees to about 78 degrees. And I can feel that the cup is just faintly warmer than the room. All right? So in the process, it's releasing that energy that was in the substance. Now the substance happens to be Epsom salt. And you know that dissolves really easy, and it's not enough to warm your bath. Why? Well, because I had to dehydrate the Epsom salt to get the water out of it, and it took a whole bunch more energy to get it dehydrated than the heat that's being released in the cup because the process is kind of inefficient. Okay, now it's up to 80. Okay, so you see we can use this simple idea of thermodynamics, the flow of the flow of energy and the change of form to explain why and how this particular real-world event actually takes place. But it doesn't always, okay, put the thermometer in first. Let's let it go back down to 70. It says it's supposed to be instant read, but it's fairly quick. Okay, so we take substance B and we dump a bunch of it in here. I put a bunch so that it happens. Now, there should be the same sort of thing. The energy driving it to dissolve should release heat, right? Okay, so now it's gone all the way up to 58. What's wrong with this picture? Okay, so when Epsom salts, endothermic and exothermic. So when Epsom salt dissolves, it releases heat. It's exothermic. When this substance dissolves, it absorbs heat. It's now gone down to 50. It is endothermic. But why is it still happening? Okay, the answer is entropy. It's actually creating more particles when it dissolves, and therefore it's more random. Thank you, John. It's more random, and it's the entropy that's driving this dissolution, not the heat. The entropy release is even greater than yes, it still releases heat, but the entropy, I said that wrong. It requires heat to get it dissolved, but the entropy release is more powerful than the heat that is required. So this is the substance that's in instant cold packs. And just in case you want to know, if you're traveling by air, do not let your instant cold packs get smushed in your carry-on bags, because it takes several extra minutes with TSA for them to figure out that it's not something bad. Really. They could think that. Okay, now let me just say there's a third one. This is a chemical reaction. This is a metal, well known, magnesium. It wants to dissolve. It really wants to dissolve. And it's not happening. You see, it's nothing much going on here. So we put a little bit of acidity in the solution. And if we're really super lucky, it'll show up. I mean, I know it'll happen because I do it every now and then, but in a minute or so, you can start to see the hydrogen gas evolving off of the metal. So the magnesium is so strongly drawn toward, I want to be dissolved, I want to be oxidized, that it will rip the oxygen out of the water. I mean, it takes a water molecule, pulls the oxygen atom out of it, leaves the hydrogen out. It doesn't care about that. And the hydrogen just bubbles off. And so you can see it's starting to get a little bit fizzy, and you can see some drop bubbles on the edge of the metal. And it gets stronger and stronger. So where's the energy coming from? Well, the energy was actually put in the fire or the electrochemical process to make the magnesium. And now I'm just retrieving a little bit of that energy back in letting it dissolve in water. And it wants that energy is so strong that it literally is able to rip water molecules apart. So what I'm pointing at is that thermodynamics, measuring all these values, has actually made all this stuff that, it's now first-year chemistry. Let's go back to the slide overheads, please. Okay, so when we look at these other devices, let's take a look at how can we use this to actually better understand and treat it as a flow-through system. Let's see, energy in real-world system flows from sources to some kind of a sink, right? That's what makes it be an open system. We can measure each part of that, and this is going to be our goal. This is how we, as inventors and experimenters, should be looking at the systems. Measure the energy within the system itself, measure what's going in, measure what's going out. And if there's something anomalous, then that should point us where to look to characterize the anomaly. I think that what's got to be pointed out is that, again, thermodynamics is not our enemy, and that the conservation laws may apply regionally, even if there is an anomalous energy source, or for that matter, an anomalous energy sink. The conservation laws in between should apply so that we can actually measure something, because that's the only thing that makes it possible to measure anything. But I want to point out too, it is conceivable that just like my substance B, that it could be entropy production as a significant component of how the system works. All right. The energy of the total energy of the system might not be constant. Well, that's true anyway. Look, you got a car. It's an open system thermodynamics. You buy the gasoline, you put it in. That's your energy input. The excess goes out the exhaust. You don't care where it goes after that. Well, we do globally, but we don't locally. And everything in between can still be a conservative system. If we say, well, that heats up the Earth, that releases stored energy and it heats up the Earth, then we draw a bigger boundary, and we can say it's a closed system. Okay, now to get unlost, I found this place where you can, if If you need to get lost, you can buy it here. Okay, compared to money. If it's a store, use the other thing. If it's a store, you should get our revenue coming in. We've got some inventory, we've got something going on here, and we also have outputs. We have losses of money. The cost of the goods sold, have to pay for this stuff. We have to pay the workers. We have to pay taxes. We have to pay rent. And we may have inputs, so the store itself should be economically conserved. You know what I mean? It should balance. The books should balance. However, from time to time, investors may put in money, and from time to time, there may be anomalous losses. For example, but like there's value in the inventory, and there's value in the bank, but there's occasions where there's also losses by theft, right? And maybe you have to invest more to replace it. Okay? The economic system, however, is a closed classical thermodynamic system on the store level, but at the national economy level, it's open. The central bank, the Federal Reserve Bank, creates money. If they want to, they make money go away. So a currency, actually. It's not the same as money. But so central banks can create money. And the same thing can be said of lending on margin. That if I put my $10 in the bank lends out 9, you borrow the 9, you go to the store, you spend it, now the store puts 8 of that back in the bank takes the 8, saves 1, lends out 7, somebody else gets it, they use 1, they take it to the store keeps 1, they send 6 back to the bank, it keeps going, that's increasing the money supply, right? Not strictly. And this is why accountancy has to pay attention, that each one of those creates also a theoretical debt that balances that fabrication of money, right? So we have a virtual value and a virtual debt that counterbalance each other, and we should think about this when we look at new energy devices. Is it possible that some new energy devices essentially separate virtual something A from something B, and that they want to get back together, and until they do and cancel that debt, then we have a polarization of time and space. And yet, in the end, they will come together in an infinitude of time. They will come back together and it will be 0 again. Just like if all the debts at the bank ever got paid, then the net would be 0. And that's why governments can create currency out of nothing, keep it in circulation as long as there's trust in the currency. But if the bank collapses, it all goes to 0. Okay, so we have this is about the only thing that's really sort of an equation, that the energy of the system, the total energy of the system, is changed by its inputs and outputs, but it contains also the internal TS, that means temperature and entropy. S is the letter for entropy. That makes sense, right? Because E is already used for energy, so we use S for entropy, because there's no S's in the word entropy. And we also have the internal pressure and volume of the gases, any compressible substances in the system. Okay, now here's where it gets interesting, and this is going to be our study of the devices. Are there any anomalous sources? Are there any anomalous sinks? Think about it this. If you had a free energy source that produced an energy sink, you had a something or other here, a box, that would absorb energy and just sit there, sort of like a very mild black hole. A very gentle one, and it would just absorb a few kilowatts. Could you use it? Everybody better raise your hand. It's like, darn, yeah, we can use that. put a Stirling engine on it, and it'll be the heat sink of the Stirling energy. I'll just suck energy from the air and have it run a generator. So an anomalous sink is just as good as an anomalous source if you want to get usable energy. Oh, I didn't tell you what to do with this. Thank you, George Wiseman, for an excellent talk last night. Yes, it's not very useful if you just put the magnesium bar in the water, but a small amount of acidity will dissolve the magnesium oxide to magnesium citrate, which then you can use. I apologize if that makes nasty noises in the sound system. Okay. So, again, Ilya he demonstrated to the world that when there's a large energy flow, it tends to create what he called dissipative structures, ripples. When you see the water go down the river and you see the ripples on the surface, those are dissipative structures. They are how the entropy is produced to dissipate the energy that's expended as released, energy released as the water goes downhill. But he says, look, this second law stuff, it seems to be more like a general concept than it is like a real physical theory. So yeah, this is what happens, but we need to know a whole lot more about the production of entropy, and he proceeded to develop a research group to do just that. Because the only thing that the second law of thermodynamics says is that the production of entropy is always greater than zero. And even this, we're going to have to question. Okay, so now to some devices that I think you all, most of you are familiar with these devices to some degree. So I'm not going to go into a long dissertation about how they work. The GEET device has been presented here at this conference many years, and we're fortunate to have David Pantone presenting. I think he's on Saturday. So we all miss Paul himself greatly. That's his loss is a loss to everyone. But he invented this device, but somehow it never could make it into commerce. But basically, it's a fuel processor to work an internal combustion engine. And so it sits between the engine and the carburetor. And here's Paul speaking at a conference a few years back. Apologize, that's a little bit of a fuzzy photo, but at least to acknowledge the inventor. Here's a GEET device. I built a couple of them, then I took his class. I built a couple of them so I'd know what he was talking about. Then I took his class and then built a couple more. So here's one that, as I said, it sits, here's the carburetor. Let me see if I can get this. The carburetor's down at the bottom, and the airflow, the airflow goes up the blue tube, and it's on the inside, and the exhaust is coming out and going, I'll switch here, going down and out the muffler. So we have bidirectional flow is transferring heat from the hot exhaust into the cool gases coming up from the carburetor. I stuck an oxygen sensor on there because I was curious how much was in there. It gets all mixed up and it comes around and goes into the engine. And so you can see here's just a typical gas engine with a generator on it. Nothing unusual there. Now let me switch back to the overhead device if you don't mind. So here's a small one. Give them a second to switch the inputs. Can you switch me to overhead? Oh, good, thank you. Okay, so here it is. This would be the fuel inlet end here going through. Here's the pipe from the exhaust and out to the muffler. And then this would be the fitting to go in, extra fittings. These things involve a whole lot more valves than it looks like. So on the inside, as you already know, is the tube that makes it possible for them to be separated, and then the reactor rod that makes it all happen. And so, there's... Now, Paul was fond of making discovering and listing out the mysteries of these devices, and the conditioned reactor rod is part of the unusual conditions that make it work. Now, rather than go into those details, let me switch back to the PowerPoint, please. Excuse me, wrong button. Okay, question. It would be, now, what does it do? We take and use either a small carburetor or a bubbler or nebulizer, and we vaporize a little bit of hydrocarbon fuel. And we run it through the GEET device, so we have fuel input, air input, go through the GEET device, runs through the engine, and has a mechanical output. Now, it would be very unusual if a little bit of gasoline would not run a gasoline engine. So that part's not anomalous. Gasoline or any other hydrocarbon is supposed to be able to run an internal combustion engine. Okay, but the question is, can we look at this system and see whether there are any unknown sources or unknown sinks? Let's use, instead of trying to commercialize it now, let's think about, can we use this as a scientific opportunity to find out whether there are unusual sources and unusual sinks? Okay, here's this same device stuck on a almost antique lawnmower. Actually, it is antique lawnmower. Here's the fuel tank. It goes through the reactor and goes into the cylinder. And yes, it runs as a lawnmower. It works. But let's look at one of the anomalies. One of the things that Paul reported is that on occasion, it can be tuned to operate with very, very little or no input. And on some occasions, and not necessarily the same occasions, these pipes get extremely cold. Okay? They're not supposed to get cold, they're supposed to be hot because there's hot gas coming out of the engine, right? So the question is, how does it get cold? Now, this is a real scientific opportunity. If we can characterize how it does this, sure, it does appear to violate the conventional laws of thermodynamics. But like I showed you with dissolving substance B, there are real-world occasions in which the system is releasing energy and yet it gets cold, right? So the question is, what's happening? Is it possible, well, we can say the energy has to be coming from somewhere. If we say that there's got to be a where, now we're coming back to thermodynamics as a science. Let's find out where the where is. Is it possible that the system is actually drawing heat from the surrounding area, 10, 20 feet around, and pulling it into the GEET processor, maybe a black hole is not, it's a suction of energy. Maybe it's not exactly like a gravitational black hole, but yes, thank you. Okay, and so among the interesting properties are as this is sitting in the reactor tube, I'll use the right one, as it's sitting in the reactor tube and spinning, it builds up charge, it builds up a magnetic field as the current flows through the device just by its own self-induction. And there may be places in which there's a great deal of ionization of the gas, and certainly Paul Pantone believes this in his what do you call it, the dealer network. And so if at some point in here we are creating the right electromagnetic environment that does something, that something is anomalous, as something that pulls heat energy from the world, the universe, then it's very interesting scientifically because it's telling something about the universe that we live in that we didn't previously know. Now the question is, can we reproduce it? If we can reproduce it, then is it coming from the ambient, which violates the second law of thermodynamics as it's classically been formulated? But that might not be the end formulation. Or is it pulling it from the vacuum? In other words, is it separating charges, separating, is there a virtual exchange particle that somehow is able to be separated and then recombine in the cylinder and produce mechanical work? Is there a virtual exchange particle that somehow is able to draw thermal energy or electromagnetic energy? Well, Richard Feynman, well known, one of the most famous physicists of the last century and great teacher of physics at Caltech, one of his great contributions was the so-called Feynman Diagrams. And the diagrams that describe how quarks and quanta and things come together, how nuclear decay happens. And he would draw these little diagrams, but they made it possible to make sense of all kinds of subatomic changes. But things like anti-electrons in his diagram simply are treated as an electron going backwards in time. Now normally heat goes in time forward, so heat dissipates out from the hot source and goes out and warms everything around it, just like rivers run downward down the hill. That's the normal direction of flow. If there's something that's reversed in time, then the heat is flowing the wrong way in from the warm places into this sink, this ball of something or other. And mathematically, it's the same, other than the second law of thermodynamics says that this ought to still require more organization. And as you know, what the second law really says is it takes more energy to clean your kitchen than it does to mess it up. Is this true? It's true of my kitchen. It's true of my desk. It takes a lot more energy to clean it than it does to make a mess. Okay, so, see, William Thomson, Lord Kelvin said, it's not possible. You can't have a transformation whose only result is to transform into mechanical work heat that's extracted from a source that's the same temperature all around. So he basically, in a fancy way, what he said is you can't have one of these. No, what he really said was he'd never seen one. And he couldn't see any evidence that anybody that was claiming one had a real one. But Kelvin was an experimentalist. He believed the experiment. And so when he saw that he could never find an example of taking the ambient heat and concentrating it and pulling it in like just a room making its own fire, he said, no, it doesn't happen. But he was an experimentalist. If you show him the experiment, if someone had shown him such an experiment, he would have been most interested. So, what we have to do is we have to measure all the inputs and then measure every single place where the energy might be coming out. And that's how we detect the anomalies. If we could get a GEET processor to run like that reproducibly, then the thing to do would be put it in a big room, connect a load onto the output of the engine, and actually measure very carefully the output of mechanical energy, and then that if the pipe gets cold, it's eventually going to make the room cold, right? So what do? We put in an electric resistance heater to heat the room, and we make the room into a big calorimeter, and then we measure the caloric input that's required to keep it going, and we see, does it balance? Does it not balance? And now we're on our way to figuring out how this works. Okay, interesting physics. May require, if it works, then we have to extend the theory, and that's a good thing. I'm going to go quickly through a short discussion of the pop engine. I think you all know we had an excellent presentation at the Kofi conference 1 or 2 years ago that went into great detail about the Joseph Pop engine. He was a Hungarian-born gentleman who, well, he wasn't entirely gentle. He was a Hungarian-born man who brought to this country this device, and here he is standing next to one of his engines. I think this engine was actually built by the Roner brothers. He was very secretive about how they ran. He never really told anybody good information. He would always start them, you know, for his potential investors, he would make them step out of the room, fill it with his fuel gas mixture, start it, and then let them watch. Okay, it has a very special design of the cylinder and the cylinder head that involves special shaped electrodes. The piston itself and the cylinder head are shaped in a way that it forms kind of a donut of space, a toroidal space within which this whatever it is happens. And here's a rather fuzzy, you can build a cylinder with plexiglass walls and take a picture of the inside and look at what's going on with the spark and so forth. The notable things, it runs on a mixture of noble gases. If they are either not consumed or possibly they may degrade very slowly, but certainly not consuming them like a conventional fuel. Yet, and this makes no sense, they react with fluorine and a few other things and the compounds last for seconds. But certainly nothing there makes sense as far as a conventional fuel. The engine did not require a cooling system. All the reports say it would get mildly warm, sometimes not even get warm. And yet it could put out 100 horsepower and it was tested on a dynamometer at least twice, one in Florida and one in Oklahoma. The Oklahoma test was for potential investors, and they certified that it was putting out, let's see, it says, it ran between 100 and 700 RPM, and down here, the output was 107 horsepower, running at 776, 700 RPM and 776 foot-pounds of torque. That's quite remarkable for a small engine, because, you know, most of the time driving your car, even if you've got a 100 horsepower engine, you're not using 100 horsepower even driving down the highway. There is a story that he put an engine into an old school bus. He used it for demonstration of concept, but because it wasn't licensed or anything, he may have driven it as much as a block or two just to get it from one place to another. But yes, this affidavit was signed and certified and notarized that the dynamometer operator really did see that. And there are some really good videos. No, they're lousy videos, but they're most interesting videos of it running on the dyno in Florida. What was happening? It could be nuclear transformation of the gases. If you add up the if U.S. Department of Energy spent an enormous amount of money measuring the energies released in every conceivable nuclear transformation and making tables of this. It probably is what kept some of the Lawrence Livermore Laboratory funded for decades. So there's tables of this, and you can get them for your computer for free. And if you look at just the energies released, it doesn't take but a minuscule amount of some nuclear transformation to release 100 horsepower. The trick is getting that to happen every stroke of the piston. Is it somehow a special spark condition that somehow pulls out zero-point energy or energy from the vacuum, or some phrase that we use for basically saying, I know it's doing it, but I don't know what it's doing. Now, his engines also, some of the engines had magnetic coils around each cylinder, around the cylinders, and the magnetic coil surrounding the cylinder was turned on and off at various points in the cycle. So, is it possible that there was some kind of resonance between this cycling of the magnetic fields, the movement of the pistons, the spark, and energy in the ambient world? So that there was some pulling, again, some ambient heat or something in for energy. There was certainly no stored gas, either a liquid fuel tank, nor was there pressurized gas. There's no way you could do this. You can't run 100 horsepower for an hour. I think the affidavit said an hour and 6 minutes at 100 horsepower. You can't do that off of hidden batteries. And you can't do that off of a hidden pressurized gas tank. It's impossible. People looked around for some kind of magnetic induction, like did he build some kind of a secret transformer that was radiating to the coils around the cylinders, and it was actually a magnetic engine hidden behind all this contraption. Well, no, he demonstrated it in all kinds of locations, and there was no way that anybody could see that he could possibly have set up inductive coils there. And for his demonstrations, Joe would actually disconnect the starting motor batteries. So you can see that in some of the videos that are online. How did it happen? Well, once again, here's where treating the system with thermodynamics and measuring the outputs, heat, electromagnetic radiation, here's where we want to know, is it coming from an unknown source? Is that unknown source nuclear? He talked a lot of blah, blah, blah talk in his patent disclosures about nuclear this and that, but he didn't really explain how it works. Okay. It's open, the energy quantities should add up. They should add up in a pop engine, they should add up in pulsed electromagnetic field motors. I'm not even going to switch to the overhead because I think you can see this. I brought a little pulsed electromagnetic field motor that you can see. Okay, it works. It's got a battery under here. And this is a motor that was of interest at this conference probably 5 years ago. So we bought a kit from the inventor at a price of about $300. And it came with all the parts, and it works. And it came with a large non-disclosure agreement that says that I cannot tell you how to make one. So I would tell you instead, look back at some of Michael Faraday's work, except that he didn't have neodymium magnets, and he didn't have a coil winding machine, and he certainly didn't have 9-volt batteries. But anyway, I'm not going to tell you how to build one. And now the question is, does this do anything unusual, right? And here's where, in our enthusiasm, I fear that sometimes we get overly accepting. Like, if it's more efficient than your average fan motor, does that mean that it's doing anything anomalous? Well, most of your average fans are run by something that looks about like this, right? Regular shaded poled 60 hertz motor. Now, if you say that your pulsed motor is twice as, let's say it runs twice as long on a battery as some other motor, does that prove that you've done anything remarkable? Not necessarily, because the efficiency of these things is terrible. Yes, you can make electric motors that have very high efficiencies, up in the 90% levels. But in general, for consumer applications, the engineers don't bother, right? Because it's not worth it. So if you're going to say that this motor is doing something really remarkable, then you've got to actually make a fundamental physics experiment. And I'm going to attempt to demonstrate how we do fundamental physics. If I'm lucky. See, because remember in our schooling that we learned about the CGS or the MKS, meter kilogram seconds system of units of measurement, otherwise known as the metric system. Okay, so we got to make the motor do something useful, like lift a rock. I'm serious. That with this, you got to weigh the rock, and you measure meters per second, meters per second. So grams of rock, meters per second, and now you're actually measuring in the fundamental MKS units, kilograms, CGS. You're measuring in fundamental units the actual output of the device. Now you can talk to physicists because you are measuring it in fundamental units. You've got to measure the energy inputs. Okay, this is a problem because measuring the depletion of the battery is marginal. Okay, you can put a voltmeter in, an ammeter in the circuit, but is an ammeter going to be doing a good job of measuring the pulsed absorption of energy by the coils? No. So again, now you've got to think about how can I put this into fundamental units. You can put a resistor in the circuit. Let the resistor dissipate heat and heat water. Because remember, 1 degree, 1 gram per cc, 1 degree, it's a joule. Right? So you've got to measure it in fundamental units, and now you can talk to physicists. And if it's doing something interesting, they'll be interested. Okay, I'm going to now launch into speculation for the last couple of minutes. Elizabeth Rauscher is a remarkably bright lady who is also a great friend to this conference. She was one of the organizers of the first Colorado Springs Tesla conference decades ago. She has also explored the mathematics of a mathematical representation of space that I think deserves consideration. It's hard to read. I don't even pretend myself to understand all of her mathematical treatments. But what she does is say, look, the way we treat time and space now, 3 dimensions plus time, actually it was Minkowski in Poland who helped Albert Einstein understand the math of how to treat time and space in one mathematical treatment. And so thanks to that, we have the Einstein's unified theory of time and space and gravity. So basically, what we use that is a 4-dimensional Minkowski space. We have 3 dimensions of ordinary distance, and time is a special dimension because time goes the other way relative to distance. In other words, when you travel a distance, it takes time. It uses up time. So in order to make time get a negative sign, when you go positive distance, you use up you absorb time, essentially, as we know, like sitting in traffic jams. You use the symbol minus, the square root of -1, so that when you take the distance value, you square all the things and make the triangle, you know, like in high school geometry class. And the square roots of -1 turn into the -1 value, and that makes it use up time when you travel distance. Well, Elizabeth Rauscher and her associates, like Amoroso, said, well, what if you allow all the dimensions to have both a real part and an imaginary part? And imaginary doesn't mean fantasy. It means that it's the complex image that makes it possible for it to go negative. Well, what if you could have the 3 distance dimensions have an imaginary part in addition that's unseen, right alongside our ordinary distance. And what if time could have a positive real part that goes right alongside our usual absorption of time when we do work or travel distance? Would it mess anything up? And the answer is no, it doesn't mess anything up. That you can still have all your conventional equations of motion in the real dimensions. You can still have the Maxwell equations for electromagnetics. They all still work in the real dimensions. In other words, we could have overlooked the imaginary parts of the distances and the real part of time all these years, all these centuries, because our usual physics would all still work whether they're present or not. But what that allows for is that while there is the real space that we observe, in a different way of turning in this case, the mathematical tensor, if you turn the tensor a different way, then things are not separate. So it's like if we have a piece of paper and a Sharpie, and we draw a line and we have some stuff on this piece of paper. And I show it to you, and I say, you can see that this is a distance. But if there's another way in which the universe is turned, and you look at it this way, it's not a distance. It's a dot, right? So the distance is real, and yet the dot is also a perfectly legitimate representation. Okay? So if I have a phenomenon here and a phenomenon here, they look distant in space, but in some other way maybe they're not. Okay? Now this mathematics, I'm not saying this is for sure true. What I'm saying is that this mathematical way of representation may give us a way of looking that helps us. That entropy production in the real dimensions may be an inviolable law. But if time and space are turned a different direction, where's the entropy? So if I have a world line that goes out and it fragments a la Prigogine, and we have dissipative structures on a real world line, where are those dissipative structures viewed on this way? Where's the entropy? They're both real. They're both legitimate. They're not separate. So I invite you to contemplate that. Think about this as a possible expansion of our view of thermodynamics. The problem with this eight-dimensional complex Minkowski space is it allows too many possibilities. It allows infinite numbers of possibilities. And therefore, the questions for us are, how can we, within that space, find out what the limitations are? Because obviously the universe it doesn't seem to be blowing up this second. So it doesn't seem to blow up every second. And by doing so, we can say that it is possible that we can find these circumstances in which energy comes into our real dimensions in a sensible way and usable way, and yet doesn't violate any physics laws, but we need to know the new laws. Like the creation of money, if it happens at all, it happens all over the place. You know, every nation can create its own money. Even villages create their own objects of trade, right? Their values. But yet once they're created, there's got to be some consistency to it. We experience that our life has some consistency to it. Therefore, if there are anomalous sources and sinks, they probably exist in lots of places that we didn't notice. Yet, the conditions in which they can happen are special. Just like only the central bank gets to fabricate money. Only the central bank gets to get rid of money. Otherwise, the economy goes haywire. So, I invite you to think that way, and I hope that this has brought some new ideas to you. I think we better be wrapping up so that our afternoon stays on schedule. So I thank you.
Thank you very much, Tad Money. If we have any questions, please come on up to the square. Oh, here we go. Run to now, run.
Okay, that's the danger of thermo.
I was going to make a comment. Nice presentation, helped me a bunch. I worked with Bob Roner for 5 years.
Yes.
One of the stories on the PAP engine, Bob built 2 of them.
Yes.
All right, and when they went and tested one on the dyno, Bob bought the dyno, took it down there. PAP hooked it up to the dyno, fired it up, but PAP always had his engine where you could move it around.
Yes.
And so if you take a 100 horsepower engine with 657 foot-pound of torque, what's it do? It turned in circles, and he destroyed one of them.
Oh,
and
no.
I don't know, I didn't know if anybody knew it. Pap was brilliant sometimes on certain things, but didn't use his brain on the other.
So he actually, he was just moving around on the cart, and the gyroscope effect overtook him. And
All right, what he did was he hooked it up to the dyno.
on the dyno.
He would always move, what he would do is when he would prove that engine, he would lift it up and show her, but it's not hooked to the floor. There's no pipes coming into it.
Right.
And so it was loose, so when he hooked it up to the dyno, and he fired it up, it went in circles.
because
and
it was.
destroyed the engine. So Bob had the other one. Bob does have that remaining one still in West Liberty, Iowa, by the way. So interesting presentation. Made me think a little bit different. So,
That's the idea.
Nice work.
So we really have to look at this like this science is our friend. We've got to use it the right way.
Yes, yes.
Okay, thank you all, and have a good afternoon.
Thank you, Thad.